Alright, well, welcome. We are going to be writing a program now to demonstrate how parallel programming works. The program we're going to write is adding all of the numbers between 0 and 1 billion. We're going to first write this program using a single thread. And then we're going to do this in a parallel fashion using parallel programming, where we hopefully are going to experience a speed up in our execution time. We're going to start off with 4 parallel threads. We'll have this as a variable in our program so that we can change that based on your specific hardware. So with 4 threads, we'll have one thread add the numbers from 0 to 250 million. The second thread will add the numbers from 250 million 1 to 500 million. The third thread will add the numbers from 500 million 1 to 750 million. And the fourth thread will add the numbers from 750 million 1 up to 1 billion. This will all be done in variables so that we can change these values very easily though. So let's go ahead and get started writing the single threaded version of this program. So open up Eclipse and let's create a new Java project. I'm going to call mine CSCI201 Parallel Threads. And now in this project, I'm going to add 2 different classes. The first one is going to be called SumNoParallel for our single threaded version. And the other class is going to be called SumParallel, and that will be for our parallel implementation of this program. Let's start off with SumNoParallel. Add your main method. Inside of this method, we are going to have 2 variables, the minimum number and the maximum number. Now the maximum number is going to be 1 billion. Java allows us to put underscores where we would typically put commas mathematically in the number. You can omit them if you would like. You cannot use commas since that's how we would separate variables being declared on a line, but you could just remove the underscores and keep the number like that. It's a little harder to see that that's 1 billion, but there are 9 zeros after that 1. Okay, let's get the current time from the system before we start doing any processing. So we'll call it before. And there's a method in the system class called current time millis, and we'll get the time after as well. I left a blank line on line number 7. We will use that. That is going to be where we put our actual processing. After we get the time before and after, let's go ahead and get the difference. And then let's print that out. Alright, now the way that I want to calculate the sum of all the numbers from 0 to 1 billion, instead of just having a for loop counting from min number up to max number and adding, we are going to be doing that. But to make this be a little bit more in line with how we're doing it with our parallel code, I'm going to create another class that is going to do this for us. So we'll go ahead and write this code here. We're going to create a class called Sum. We'll instantiate it and pass in the min number and the max number. And then on that class, we are going to call a method compute. And that will just add up all of the numbers from min number to max number. To wrap up the main method, the last line let's just print out what the sum came out to. So the sum from min number to max number is num. Now the reason that I do that is because I want to make sure that what we are comparing is correct, that we actually are adding up all of the numbers correctly. So let's just print it out so we have our answer, and then we can verify that it's correct. Alright, let's go down to the bottom of this file. I'm going to create my sum class here. Remember that Java allows us to have more than one class in a file as long as only one of them is public. So here we're going to create two variables inside of this class, min_num and max_num. We'll make them private variables. Create your constructor that takes min_num and max_num as parameters. Store them out into your member variables. Now we'll create our compute method. In our compute method, this is where we're going to do just what you would expect for adding up all of the numbers. So we will just iterate from min_num up to max_num. Oops, I needs to be a long instead of an int, since those are long variable types. Just add i's value to the previous value of sum each time, and then return sum. Notice that I'm having the compute method return the object long instead of the primitive type long. This is going to come into play when we have our sum parallel example. For now, this is going to work though. The reason this works is that Java has something called auto-boxing. Auto-boxing is where a primitive data type will automatically be converted to its equivalent object type and vice versa. So this sum variable that I declared on line 24 is the primitive type long. It'll automatically be converted into the long object type when it's returned. If we scroll back up in our code where I get the value of compute back, this method call here is going to return the long object back, and it will automatically convert it back to the primitive data type. That's called auto-boxing. Alright, now that we've got all of this, save your code. Let's give it a shot. Let's run it and see what our actual time is. First off, make sure that you're getting the sum to be 5 followed by 8 zeros with another 5 followed by 8 zeros. That is actually the answer when we add up the numbers from 0 to 1 billion. So make sure that that number is correct first. Then you see your time. In my case, my time was 1,546 milliseconds. Your time could be vastly different than that, faster, slower, or maybe about the same. This time is based on a lot of different parameters. This is based on your operating system, your hardware, your CPU, the amount of memory you have, how many processes you have running, what's happening on your computer right now. So don't worry if your time is faster, slower, or about the same as mine. What we want to see when we write our parallel code is that the time goes down on your computer. So what I want to do right now is I want to run the program a few more times. And I want to kind of get an average in my mind, in my head, of how long it takes to run this program with no parallel threads. So this time I'm in the 1200s. My third time I'm in the 1600s. Fourth time I'm in the 1600s again. Fifth time I'm in the 1100s. Sixth time I'm in the 1500s. So if I were to take an average there, I'd say that I'm probably somewhere in the 1300s is my time. So just get a sense of the average on your computer so that now when we write the parallel code, we're hoping to experience a speed up in our running time. That we want to see that our actual time to compute this is going to go down. So let's jump over now to our sum parallel. Our sum parallel is going to have some, if you don't mind the pun, parallels between this and what we did in the sum no parallel example. Let's add our main method in. We're still going to have our min number at 0 and our max number at 1 billion. In addition, we're going to have a num threads variable. This is going to start off at 4. We're going to be able to change this. We're going to use this variable throughout our code, so we can change this if you want to see how your program is going to execute with a different number of threads. Let's get our system time before we start doing anything. Get the system time after we're done. Get the difference. Print it out. Okay. On line 8 is where I'm going to put the actual code for separating out the threads into our different parallel threads, and then actually starting those and getting the answer back. Before we do that though, let's go back to our sum no parallel, because our sum class is going to look very similar to the one that we have right here in sum no parallel. So what I want to do, I'm going to grab all of this code right here. Actually, instead of doing that, what I'm going to do, we just need to have this sum class be a parallel thread. So let's do this. Let's just have this sum class extend recursive task, passing in a long variable. Now you have an error because this class needs to be imported. Put your mouse over it, import java.util.concurrent.recursive-task. You'll have a warning on your class now because recursive task implements the serializable interface. We're not doing anything with serialization right now, so the warning isn't going to have an impact. If you want to get rid of the warning though, you can just create the serial version UID variable, public static final long, and set that equal to some value. That gets rid of the warning. Like I said, we're not doing anything with serialization in this code, so it's not going to make a difference if that warning was left. But I like to get rid of the warnings if possible. Now this isn't going to change the execution of our sum no parallel, because we're not actually starting any recursive task. We're not starting a parallel thread. So our sum no parallel is still going to execute exactly the same. Now you see my reason for naming that method compute and having it return a long value. The recursive task class is a generic, so we have to pass in a type to it. We passed in a long. That value has to, or sorry, that type has to match the type that's returned from the compute method. Recursive task is the class that returns a value from the parallel thread. Recursive action was the class that doesn't return a value. In this case, we actually want that value back. We're splitting our sum into 4 different threads. Well, after each one of those threads adds up its set of numbers, we then need to add up those remaining 4 values so that we get our overall solution. So that's why I need that value returned here. Now we're going to just utilize that sum class in sum parallel. So let's go back to sum parallel. Inside here we're going to create a fork join pool object. Remember that fork join pool is the managing class for parallel threads. It would be equivalent to the executor service in multi-threaded code. The fork join pool has a constructor that takes no parameters. We just need to import the fork join pool class. So I'll use our little Eclipse shortcut, Control-Shift-O. It'll automatically add the import at the top for me for fork join pool. Next, what I want to do is I'm going to create an array of 4 elements, the number of threads, of type sum. So that class that we just had from our sum no parallel, I'm going to create an array with num threads size. Now, this is going to be 4 threads to start, and I want to set each one of those threads to add up a different set of numbers. Well, fortunately, the way that I wrote that sum class, it takes a min number and a max number as parameters in the constructor. So if I pass 0 and 250 million into one instance of sum, it'll only add those numbers. If I then pass 250 million 1 to 500 million into another instance of sum, it'll add that set of values together. So now we just need to programmatically do that. I don't want to hard code these values because if we change the number of threads, I want it to automatically adjust the set of numbers that are being passed in to each one of my sum objects. So we'll start off with the first thread is going to start at min number, and it's going to end at max number divided by num threads. So the first thread will start at 0 and end at 1 billion divided by 4, which is 250 million. Then I'm going to iterate through the number of threads that I have. Let's instantiate each one of them to go from start to end. Now after I instantiate it, I need to start it. This is where my fork join pool comes into play, and I'm going to call the execute method. Remember, the execute method on the fork join pool just starts that thread. It forks that thread, which puts it into a different core on your computer, and it'll execute that thread. It's not going to wait for the return value to come back. So we're going to have to join against that thread in a minute here. We'll do that after this for loop. Now that's going to get the first thread started. We still have 3 more threads to start. So the next step is that I need to adjust my start and end. Well, start's very easy. It's just going to go and be 1 more than end. End, we're just going to add another max number divided by num threads to it though. So start for the second thread will become 250 million 1, and end is going to have been, it was 250 million, and we're going to add another 250 million to it. So it's going to become 500 million. This will go through for each of the 4 threads that we have, and we'll cover the entire range from 0 to 1 billion. Now, at this point in my code, all 4 of my threads are executing. They're in different cores in my CPU or different CPUs based on your specific hardware. If you don't have 4 cores, then it's going to send those threads to as many cores as it can, and the rest are going to operate in a multi-threaded fashion within the cores where more than one thread was sent. So now those threads are all executing. What I need to do to get my answer in this num variable, I need to wait until all of those threads finish executing so that I can put them back into that variable num, add them all together. So what I'm going to do is iterate through all of my threads again. And then I just need to join on each one of them. So I'm going to say num plus equals each one of my threads dot join. Now the join method is going to return whatever comes back from compute. Now in our case, we're having compute return a long value. So this method is going to return the long value to us. We're just going to add to the previous value of num. To wrap up our code, let's just print out that value again to make sure that everything is working correctly. All of our threads have come back properly. So let's say the sum from min number up to max number is the value of that num variable. Okay. So that'll just make sure that we're getting the proper value here when we run this code. All right, I think that's all that we have here. Let's go ahead and run this. Let's keep our fingers crossed that we get times that are less than the one that we had before. So my average time was about 1300. Let's see what happens when I run this in parallel. Oh my word, got it down to 526 the first time, and you see that my sum is still correct. So that brought it down, gosh, to about 33% of my running time, a little bit more, maybe about 40%. Let's see the next time. 474, 541, 512. So let's see, I'm going to run a few more times just to get my average in there. 672, 504. So it seems like I'm probably somewhere around 500. So I was at somewhere around 1300. I brought it down to about 500 with 4 threads. That's a pretty good improvement that I have there. Now, it's not going to be exactly 25%. You may have thought we have 4 threads, so why doesn't it bring it down to 25% of the runtime when we had 1 thread? Well, the reason for that is because there's overhead in forking these threads. In addition, even though I have a dual core processor on my machine that's hyper-threaded, so my operating system thinks that I actually can have 4 threads running at a time. I really can't. There's only 2 threads actually running at a time, and each one of my cores is then switching the other thread in and out very quickly, faster than the operating system can. But it's still not 4 threads that are all actually running at the same time. Now you can play around with that number, the number of threads that you're using up there. Everything is with a variable, so you can change that from 4 to 8 to 16, 32, whatever number that you want. If you'd like also, you can figure out programmatically how many cores you have on your computer. Inside of the runtime class in Java, you can get your current runtime, and there's a method called available processors. Available processors is going to return the number of cores that your operating system believes you have on your computer. It's not going to return the actual number of processors or cores. It's going to return to you how many the operating system believes you have. So in my case, it's still going to return 4. If you want to print that out just so that you can see how many cores your operating system believes you have, let's just print that out right here. Save it, run your program again. You'll see it prints out 4 for me. So you can play around with that number too. That's telling you the number of cores the operating system believes that you have. Hopefully you've enjoyed this program. It's shown you the power behind parallel programming. There are other parallel programming algorithms that exist out there. One that's a little bit larger that many of you may be familiar with, merge sort. Merge sort would work very well as a parallel algorithm. It's a divide and conquer, which is where we can experience a lot of speed up. So if you want, take a look at a merge sort. Write a merge sort with a single thread, and then write merge sort with parallel threads so you can see what the improvement is going to be.